Let us start the second talk of the session today, which is by John Martyn.
All right, am I good? Okay, cool. Well, hey everyone, I'm very happy to come out here and speak. And today I want to share with you a really interesting story in which we can use randomization, specifically through incoherence, to benefit quantum and classical algorithms. And in the instance that I'll show you, we use only a little bit of randomization. So we're not randomizing over things that are very far away from each other, but rather we're randomizing over things that are highly or tightly concentrated with each other. So it's kind of surprising that adding this like a little bit of randomization does improve these algorithms, but I want to walk you through how that works in both the quantum and classical context, and then maybe discuss ideas for the applications of this going forward. So in quantum information, we typically deal with coherent states, such as pure states evolving under the Schrodinger equation, as I've shown here. And typically we'll view noise and randomization as kind of like undesirable features that we want to get rid of. So for instance, these lead to things like mixed states and decoherence. And as an example of this, in quantum error correction, as Jonathan spoke about, we tend to see this as a problem that we want to remove, and so we remove that decoherence in pursuit of coherent quantum dynamics. But what I want to talk about today is actually going contrary to this. So I want to show you that incoherence in small doses enhances the quantum and classical algorithms. And it's kind of surprising, you can prove this is indeed the case. And so I will show this in two contexts. In the first context, I'll focus on quantum algorithms through a framework known as quantum signal processing. And in the second context, I'll focus on classical methods, specifically with these neural network quantum states. And I hope that this is of interest to like the audience here because you guys work on both quantum methods and classical methods. And in each of these cases, I'm only going to use a little bit of incoherence. So like I said earlier, we're not randomizing over things that are very far away from each other, but rather things that are tightly concentrated. So what I mean by that is like the mixed states that we will consider are very close to being pure, but they're not exactly pure. And the punchline is that this little bit of incoherence does go a long way in improving these algorithms. And I really want to show you that. So without any further ado, in this talk, it'll be the methods that I will introduce are based on our main ingredient here, which is known as randomized compiling, which is a tool you can use to randomize over quantum gates to suppress error. And it's a general tool, and I'll walk you through how that comes about. And then with our main ingredient, we'll cook up two dishes. First, I'll show its utility in quantum algorithms, specifically how it reduces the cost of quantum signal processing algorithms by a factor of 1/2. So if your algorithm beforehand would take, say, an hour, now it takes about 30 minutes using this randomized method. And in addition, I'll cook up another dish where we'll show its utility in classical methods, where we'll show how we can use this to improve the accuracy of neural network quantum states in approximating ground states. So if your neural network quantum state approximates the ground state to within like 10%, if we use our method on top of this, we can get an even better approximation to say like 1%. So enhance that accuracy. So let's first jump into our main ingredient, which is known as randomized compiling, which as I mentioned, is a method of randomizing over quantum gates to suppress errors. So this is based on a central problem in quantum information, which is we want to approximate evolution under some unitary V. So that is, we want to take a state rho and map it to V rho V dagger. As an example of this, time evolution considers V to be e to the minus IHT, that is the time evolution operator, and we have like a whole swath of algorithms for approximating this transformation. And the conventional solution for solving this problem is to approximate V with a unitary U. You approximate V with some unitary U that's close to within some norm, like the matrix norm, for instance. And then you evolve rho under U, and that should provide a good approximation to your desired state, V rho V dagger. As an example of this, in trotterization, we consider a Hamiltonian that breaks into, say, two terms that don't commute with each other. And then we take as our U evolution under A and B, under small time steps, and we repeat this many, many times. That is like the trotterized evolution. And this approximates e to the minus IHT pretty good if this value of R, that is the number of trotter steps, is quite large. And then we just imagine applying U, that is our trotterized evolution, to our state. And this provides a good approximation to our time evolved state. But what I want to show with you guys today is an alternative solution in which we average over many approximations. So that is, we take rho and we map it to a probabilistic mixture of that state evolved under some approximations Uj. So like Uj rho Uj dagger is some approximation to our desired state V rho V dagger. So specifically, each one of these Uj's approximates V, and Pj is some chosen probability distribution. And so this is like an average over all of those states that we get out of this. And this itself is known as randomized compiling. And as I will show you, it can actually outperform any individual approximation. So by considering this state here, this can approximate our desired state better than evolution under just one single uj. And it comes from averaging over many of these approximations. And you should also note that this is actually a quantum channel, because in the conventional quantum mechanical lore, we can implement this by sampling an index j from this distribution pj, then executing uj on our quantum computer. So whereas in ordinary compiling, we'll approximate our transformation with some deterministic unitary and just evolve under that, what I'm saying here is we take an average over a bunch of different unitaries of u1, u2, u3, and this does better than this case. Yeah, go for it.
That's the question. Do you need to worry about making sure that all of the approximations are equally bad?
They don't have to be exactly equally bad, but that is literally on my next slide, so I will show you where it comes from. So as I mentioned earlier, randomized compiling can outperform deterministic methods by suppressing errors. And this is quantified through something known as the mixing lemma. And let me explain what the mixing lemma is. So let V be our target unitary that we want to approximate. And suppose we have an ensemble of approximations, uj, where each one of the uj's approximates V to within some error epsilon. So that's the answer to your question. And so if we evolve under uj, then we suffer an error that scales like O of epsilon. So it's linear in that error of the individual approximation. However, if we can also find a probability distribution such that if we average over the unitaries, that is literally averaging over the matrices, and that deviates from our desired unitary V in spectral norm by O of epsilon squared, then it turns out that we can show that the associated channel, that is Pj, Uj, rho, Uj dagger, as I showed before, approximates our desired state to within O of epsilon squared accuracy. And this holds for any input state rho. And so what's fascinating about this is that this affords a quadratic suppression of error. So if epsilon was like 10%, we can now suppress that error to 1% at the cost of just randomizing over the approximations that we end up applying. Now, this might be kind of like confusing where this quadratic suppression of error comes from, but there's an intuitive picture for it. And it is that randomized compiling achieves this quadratic suppression by randomizing over the errors. So normally, if we do things deterministically, say we apply a unitary that suffers some error, and we consider n fixed errors, then if things are done coherently, those errors can add up constructively to a total error that's like O of n. And on the other hand, if we randomize over these errors, that is, we randomize over their sign and their value, then they effectively perform a random walk. And as you might recall from statistical mechanics, the standard deviation of a random walk scales like O of square root of n. So that's sort of where this quadratic suppression of error comes from, and that we're now randomizing over the errors such that an expectation is lower than in the coherent case. Now, to really convey to you intuition behind this, I want to go over just one quick example here, which is how we can use randomized compiling to reduce the error of first-order tritorization. So in first-order tritorization, the unitary we want to approximate is evolution under Hamiltonian that decomposes into A plus B. And we want to do that for some small time step delta t. And if we consider first-order tritorization, we can either approximate this time step as evolution under A and then B, or evolution under B and then A. And these are both equally good in that they both suffer error that's O of delta t squared. And then you can also show that if we average over these unitaries with equal probability, so both 1/2, then that average suffers error that's O of delta t cubed. So in this summation, the second order errors actually cancel out. And so now we get an error that's smaller than we had in the deterministic case. And so then by the mixing lemma, you can show that the corresponding randomly compiled channel suffers error O of delta t cubed. And what's interesting about this is that this achieves the same level of error as a second order Trotter formula, that is O of delta t cubed. But the price is that of just a first order Trotter formula, because we're either randomizing over this formula or that formula. And the errors cancel out on average such that we do better in expectation. Okay?
So if I go beyond the first Trotter step, but I just show some arbitrary cutoff in the nested commutations that I want to compute, or bigger can be after. Does the error just scale with the orders that I pick? So in principle, I could like just choose like some super big cutoff and just sample from it. What's the cost? Do you have a smaller? Yeah. How does it?
Could you clarify the question? Do you mean like, does this work for other high order Trotter formulas?
Yeah, exactly. I mean,
Yeah.
I now take a unitary, I go to like, some big Hausdorff expression. So choose a cutoff or something, and then you just like, and I'm just gonna sample which of the lower order nested commutators I'm gonna actually compute and then implement.
Yeah, so there is a method of doing this. It came out in a paper that I think was published last year, and I'm happy to send it to you if you're interested, but there is a way of considering the higher order errors, that is like the higher order nested commutators in the Trotter formula. And by taking those into consideration and appropriately randomizing over things, you can promote an order n Trotter formula to an order 2n Trotter formula. So like you really only apply order n Trotter formulas, but you do it randomly and use some correction operations, such that the resulting channel achieves an error equivalent to that of an order 2n Trotter formula.
And that's also then randomly compiled.
It's randomly compiled, but the construction is different from what I've shown here. It's more involved, but like for first order, you can just simply randomize over the order of the terms you're applying, and that does promote you to second order Trotter. Okay, good. Okay, so the main takeaways are that we achieve a quadratic suppression of error by randomization. That is, we go from error like epsilon to error O of epsilon squared. And because each one of the unitaries that we're randomizing over, each approximates V, the channel here is close to unitary. And so as a result, we only use like a little bit of incoherence. And so that's what I mean by that. That's what I mean by we're randomizing over objects that are tightly concentrated to each other. Each one of the UJs, they don't differ from each other by all that much. And then I will also mention that this construction does extend to quantum states. So if we want to approximate a pure quantum state V, that is like a ground state of a Hamiltonian, we can consider a mixed state that is an average over a bunch of pure states that are good approximations of V, such that that mixed state approximates our desired state, or desired density matrix, to within O of epsilon squared error. So it's literally the same construction, now just transferring that intuition from unitaries to quantum states. And so the overall message is this kind of crazy statement that doesn't seem correct, but it is. To approximate a unitary, use a slightly non-unitary channel. And to approximate a pure state, use a slightly mixed state. It sounds really crazy, but it turns out to actually be true. And I'll show you some instances of this. Okay. Are there any questions before I go on to applications?
This only works in trace distance.
Yeah, this is in trace distance. In fidelity, you do not get an improvement.
Yeah.
That is a good point. But in trace distance is often a very relevant quantity because that determines the error in observable. And like, if you want to compute some observable at the end of the day, then this is the metric you want to care about. But good point. Yeah. Yeah.
Does the suppression of error scaling, it depends on this choice of probability, right? Because
It does.
there's
Yeah, so you need to find a P that obeys this condition. But if you can find a P that obeys that condition, and if you know what the structure of UJ is, it's often not too difficult to do so, then you can achieve this quadratic suppression. So, do you have a question? Okay, very cool.
sorry, can I follow up?
Yeah, go for it.
The Hamiltonian cauterization error, the scaling is delta T to the cube rather than 4. So is that because you chose like a particular?
That is a very good point. This is a bit of me trying to be a bit too cavalier here. This is not full quadratic suppression. This is from O of delta T squared to O of delta T cubed. But suffice it to say that in principle, one could achieve a full quadratic suppression. So this is really like to the power of 1.5 suppression. So yeah, good point.
So like you can choose another combination of P
Yeah.
to achieve that. Do you know like how to achieve the optimal?
I do know how to. It's actually not this construction here, and it's slightly more involved, and it does involve these higher order commutators, as Jonathan mentioned, but it can be done. And again, it's in that paper that I was just mentioning, so I'm happy to send it to you if you're interested. Okay. Yeah.
And this mixing lambda is also valid for the states instead of for the unitaries, let's say.
Yeah, so it also does
Like
apply.
that, yeah.
It applies to the states in like the analogous way. So you want each one of the UJs to be close to your desired state, and you want their average to be even closer.
And so I can consider instead like of the combination of the projectors, simply combination of the pure states.
Yeah, so it's actually a linear combination of pure states. So it's not a density matrix. It's literally like you're averaging over vectors. And if that's closer to your target state, then you do achieve this quadratic suppression of error. But the fact that we're averaging over pure states is just like a property that you want to satisfy such that the mixing lemma does hold. But like that's not what you do quantum mechanically, because really we're averaging over density matrices. But I have this, I have the written up if you want to look at that a bit closer. Okay. Yeah, go for it.
If you ever have to work with pseudo-probability distributions, and so you have some degree of sign problem, is it ever worth to opt into it? Or the second you're not working with proper distributions, you should just not do it?
You know, I'm actually not sure if this works in the case of quasi-probability distributions. I would imagine that it does, but I really don't know the conditions of it. That's a good question. I think it ought to be okay. I would imagine it probably does work, but I would need to like think through it for a bit. Yeah. Okay, cool. All right. I will go on to applications, and we will first cover applications to quantum algorithms, which is this really fun paper I worked on with Patrick Rowell at IBM, where we show we can cut the cost of algorithms in half by using randomization. So, as you know, many companies are interested in, and many people are interested in, quantum algorithms can provide advantage for a large class of problems. These include things like quantum simulation, that is simulating the dynamics of the Schrodinger equation, say search, that is searching like a database for a marked element, and also things like factoring integers and solving linear systems of equations. And in quantum algorithms, one might wonder how can we use randomization to our benefit. And indeed, I will point out that randomized compiling has found use in quantum algorithms, and specifically in quantum simulation algorithms that are constructed by Trotterization. So like I mentioned earlier, there are existing constructions for randomizing over Trotter formulas to suppress their errors. And in talking with Patrick, one thing that we were interested in is, can we extend the utility of randomized compiling to further quantum algorithms beyond just quantum simulation and beyond just Trotterization? And the thing that came to mind is to use quantum signal processing, because this is actually a general tool for designing quantum algorithms that has very broad applicability. And it encompasses like many of the known quantum algorithms that we have today. And so the idea is, if we could apply randomization to quantum signal processing to improve it, this would apply to like a broad range of quantum algorithms beyond just quantum simulation. So let me discuss briefly what quantum signal processing is. And at a high level, it's a framework for implementing polynomial transformations of an operator or a matrix. We're here I'm denoting that operator as A. And you can think of A as being like a Hamiltonian or just like some matrix that you want to manipulate. And the polynomial that you get out of this algorithm could be, something like a squared minus 2a plus 1. But it's like in general some polynomial, and like maybe even some polynomial that Jonathan was interested in his talk. And we can actually tune that polynomial to be a polynomial that we want to implement. So very briefly, this is actually realized by an interspersed product of a rotation about the z-axis through some parameterized angle phi, and it's operating here that encodes your matrix in say its upper left-hand block. So this block encodes your matrix of interest. And what you do that if you consider this product of say rotation, block encoding, rotation, block encoding, then at the end of the day, you get a matrix out of this that encodes a polynomial transformation of your operator A. And importantly, this polynomial that you get out depends on these angles phi, but it can be like kind of nearly arbitrary. We have a lot of flexibility in what we can generate. And in addition, for a desired target polynomial, we can determine what these phases are that correspond to that desired polynomial. So if we want to implement, say, a squared minus 2a plus 1, we can classically determine those phases, and then put that into our quantum computer and get out that polynomial. And there's an important point to note here, which is that the cost of realizing a degree d polynomial is d queries to the operator A. So d calls to this guy here. And intuitively, this arises because things are being multiplied in this expression, and if we only have a instances of d, we can only generate a to the power of d, and hence a degree d polynomial. But this point will be very important, so that the cost of realizing quantum signal processing is the degree of that polynomial. And why this is useful is that many quantum algorithms can be derived through quantum signal processing by classical polynomial approximations. So if we wanted to look at a problem like Hamiltonian simulation, then what we want to realize is e to the minus iht, and this of course decomposes into cosine of ht and sine of ht. And if we want to achieve this with quantum signal processing, we need a polynomial that approximates this function here. And because both cosine and sine are smooth functions, they have like well-behaved Taylor series that we can expand and truncate at, we can approximate those as polynomials. And indeed, if you want to approximate this function to within some error epsilon, the degree required scales as O of t plus log 1 over epsilon. So if you want a, say, larger time, then your degree needs to increase. And if you want a better error that is a smaller epsilon, your degree also needs to increase. And as I've shown here, we can get good approximation to cosine by using polynomials. And similarly, this is actually exactly what Jonathan mentioned. If we want to do something like thermal state preparation, we want a polynomial that approximates e to the minus beta h. And in this case, we can again approximate this with a polynomial whose degree increases as square root beta times log 1 over epsilon. So if we want to push to larger values of beta, that is smaller temperatures, we need a larger degree. And similarly, if we want a smaller error, we also need a larger degree. Okay? And this also extends to other things like quantum research, factoring, linear systems, and beyond. Now, if we take a look at these polynomials, we'll notice they have one thing in common, which is that their degrees both scale as log 1 over epsilon.
But this was actually something I was confused about, because like in the second function you want to approximate, beta behaves like IT in the first
It's different,
so
yeah.
why is it that?
Yeah, one
in
is, it's because this is the e to the IHT is oscillatory. E to the minus beta x is not. So like you kind of need to be careful about like analytic continuation here. But very good point. I should have a footnote for that. I've been asked this before. Okay, so the cost in both cases scale as log 1 over epsilon. And this is actually a very generic feature of polynomial approximations to smooth functions. And I won't go into technical details, but the proof rests on like Chebyshev polynomials. But suffice it to say that if you want to approximate a smooth function that is continuous and infinitely differentiable, then the degree of the polynomial you need scales as log 1 over epsilon. And that can be shown. And so as a result, the cost of, in general, most QSP algorithms that we're interested in physics scale as O of log 1 over epsilon. Okay? So this is how the error scales, or how the cost scales with the error. So the question we have is, can we enhance QSP with a randomized compiler? And this would be great because, as I mentioned before, this would apply like the whole suite of quantum algorithms, like simulation and search and factoring and whatnot. And the answer is indeed yes, and we can do so by just sprinkling in a little bit of incoherence. And the approach that we'll take is to randomize over the polynomial approximations that we use in approximating some desired function. And intuitively, we imagine this could quadratically suppress the error suffered by these polynomials. So we go from like an error epsilon to O of epsilon squared. And because, as I just showed you on the previous slide, the cost of these QSP algorithms scale logarithmically with the inverse error, this is equivalent from going from a, say, degree d polynomial to degree d over 2 polynomial. And it just follows from this expression here. And so, in anticipation for the result, we cut the cost of these algorithms by a factor of 1/2 by using randomization. And this is where it comes from. And the picture to have in mind is that in standard quantum signal processing algorithms, we'll apply a single polynomial p of a to our input state, and the cost of that is the degree of that polynomial. And what we do is we introduce stochastic QSP as a randomized version of this. And in this, we apply some polynomial pj with some probability pj. And as I'll show you, the cost of that is 1/2 times the degree of that polynomial. And so here, again, we're averaging over many of these polynomial approximations. And that's what it kind of looks like schematically as a quantum circuit. Okay, so in a bit more detail, in QSP algorithms, we wish to evolve under some function f. And this function could again be like e to the IHT in the case of time evolution. And typically with standard quantum signal processing, we'll construct a degree d polynomial that approximates our desired function to within some error epsilon. And at the end of the day, the total error is going to be O of epsilon as well. And what we show in our work is how we can reduce this cost by designing an ensemble of polynomials, pj, that each approximates this function to within like roughly the same error epsilon, but whose average approximates the function even better to within O of epsilon squared. The construction is again a bit technical. It's in the appendix and I'm happy to show you guys it later if anyone is interested. But suffice it to say that each one of these pj polynomials is an approximation of a different degree. So you can imagine approximating f with like a degree 10 polynomial, a degree 15 polynomial, a degree 20 polynomial. And as you increase the degree, the approximation will get better and better. And it turns out that if we randomize over these polynomials strategically, in this, that average does better than the individual case. Because the average contains those higher order terms, whereas the individual case doesn't necessarily. And by the mixing lemma, this suppresses the total error to O of epsilon squared. So we're just averaging over polynomials of different degree, but whose average degree is much lower than the degree of the corresponding deterministic polynomial.
Sorry? Are these probabilities perhaps, are they derived from the coefficients of the polynomial?
That is genius, yes they are.
Because then that's basically a pseudo-probability, right?
Actually, I think it is, yeah. I have this in an appendix slide and I can show it to you later. But it's like literally your importance sampling the terms in your Chebyshev expansion of your function.
One more?
And what's that?
One more?
So it's the absolute value of the coefficients. So yeah, if like one coefficient is very small, you're less likely to sample that term. And you can show that these coefficients decay exponentially, such that the average like concentrates pretty close to the truncation point. And I have slides on this and I can show it to you, but that's exactly the construction. And it turns out that the average degree of these polynomials, that is pj times the degree of these polynomials, is d over 2 plus O of 1. Where this d over 2 again comes from the log 1 over epsilon scaling with this quadratic suppression of error. And this O of 1 term depends on the function f of x, but it is indeed still just a constant, as we show. And so the ratio of the costs, that is the randomized cost over the deterministic cost, goes to 1/2 in the limit of largest degree. And hence, as I said earlier, we have the cost of the underlying algorithm. So this is like the cost reduction factor. So that's all cool theoretically, but let's see how it works in practice. Oh, sorry, before I get to that, the picture to have in mind is, again, in standard QSP, the cost is just the cost of the single polynomial, which is the degree b, whereas the cost in the randomized case is the average degree of all of these polynomials. And it turns out that that average degree is about d over 2, which is smaller than this degree. So that's like intuitively where it comes from. All right, so now let's show some applications. As I mentioned earlier, because QSP is a broadly applicable tool, this applies to many algorithms of interest. One of these is, say, quantum simulation, as I mentioned earlier, in which our function is e to the minus IHT. And indeed, if we apply randomized quantum signal processing to this, we can show that the cost reduction decays to 1/2 in the limit of large degree, where the rate at which it approaches this 1/2 depends on the time, but indeed does scale as O of 1 over d. So that verifies our main theorem. And in addition, we can also consider applying this to thermal state preparation, in which case the function we want to implement is e to the minus beta h. And again, we see similar decay to 1/2 as the degree increases. Although, interestingly, it can decay from beneath it, and that's because that O of 1 factor can be negative in some cases. But asymptotically, it still approaches 1/2. And then moreover, we also show how this applies to other algorithms, so things like ground state approximation and matrix inversion for solving linear systems. We also get this similar decay to 1/2 as predicted. And so overall, what I want to pitch to you with this idea is that we achieve this cost reduction for a very wide class of algorithms just by randomizing over the approximation that we're applying through the lens of randomized compiling. So that's the ultimate punchline of this part of the talk. Okay. And then let me
So actually, can you go
Yeah,
two
go for it.
slides? Go.
This one?
Yeah. So in this case, like, it seems that your notion of cost is like expected cost.
It is. So it's the cost that you would incur in practice in a quantum algorithm.
Oh, okay.
It's
So
like
why is that a
typically-
relevant notion for practice? The expected cost rather than like the max cost.
Yeah. It's intuitively because when we run a quantum algorithm, we want to extract some observable. And to extract an observable, you need to take many measurements. So you need to run your circuit many times. Right? So like, if we're doing Hamiltonian simulation and we want to estimate like, say an OTOC or like some observable at the end of the day, you can actually run an experiment many times. And deterministically, you'd run the same circuit every time. But here what we're saying is run a slightly different circuit every time. And then expectation, that does better than the deterministic case.
Right. Okay, so this is most applicable in the applications when you need to like measure and observe.
Yeah, but I think like typically you want to measure an observable at the end of the day. Measure something. Right? So
I guess that there are also like these other short type algorithms that don't work by measuring also.
yeah, I guess if it's like a one-shot algorithm, it wouldn't necessarily work in that case because you could sample like a poor approximation. But in these ones where like you want to estimate an observable of a state or like a physics-focused algorithm, then the cost would be this average cost. But yeah, good point. Okay. Before I go into classical stuff, are there any questions? I could probably take one or two. I think I'm pretty good on time. Otherwise, I'll talk about classical stuff. Okay, so our second dish is how we can use this tool in classical algorithms. And this is a fun project that I worked on with D here, and it's how we can enhance neural network quantum states by using randomization through randomizer real-time dynamics. And so, in addition to quantum algorithms, of course, classical methods are very valuable tools in simulating quantum systems and are still state-of-the-art, maybe even relative to some quantum simulation algorithms today. And so what I want to show you is how these can also benefit from the same tool of randomized compiling in a very similar way. And what we'll focus on are variational methods for approximating the ground state of a Hamiltonian. And how these work are, we take some variational wave function that we can store classically on a quantum computer, on a classical computer, and we'll call it psi sub theta for some parameters theta, and we'll take this state and we'll minimize its energy with respect to these parameters. And this is justified by the variational principle, which states that the energy of an arbitrary quantum state is always going to be greater than the ground state energy. And so if we minimize this energy to something very close to the minimum, it should provide a good approximation to the ground state heuristically. And this is used in many instances like tensor networks and neural network quantum states and beyond. And recently, folks have developed these neural network quantum states in which you parameterize your variational state by some neural network, and then you tune over the parameters of the neural network to minimize the energy and approximate the ground state. And there are many architectures for doing so. And when you have an optimized neural network quantum state, you would want to estimate an observable or like the energy of some quantity of interest. And you do this with a tool known as variational Monte Carlo. And how this works is you express some observable, here I'm looking at the energy, as an average over configurations sampled from the square of the wave function of something known as the local energy, which is given by this expression here. And so basically, like when you have your optimized wave function, you draw a bunch of samples from it, and you compute this classical, this empirical mean, and that provides a good approximation to that corresponding quantum observable. And this has been very successfully applied to many systems in like condensed matter and chemistry and in high energy physics and beyond. But in deploying these methods, there's actually kind of like a disparity that arises. And it is that during optimization, the energy is often a lot more accurate than other observables. So here I've plotted a characteristic instance of this, in which we're studying just like an Ising model on 12 spins, so we can compare exactly with the exact solution. And I've plotted here the energy, the error in the energy in green as a function of iteration throughout optimization, and the error in a connected correlation function given by this expression here in orange. And what you'll notice that the error in the connected correlation function, well, both errors do decrease with iteration. The error in the connected correlation function is significantly higher than that of the error in the energy. And this is kind of a concern because, like, yes, we do want to minimize the energy, and the ground state energy is of interest to most problems. But there are other quantities that are also of interest, like magnetization and correlation functions and such. And so it'd be really great if we could, like, push down this error in energy, or the error in correlation function, down to the level of that of the energy. And I'll show you how we can do that with randomization. But before getting to that, let's see why this disparity arises. And to see this, we consider a state that's very close to the ground state. So let's denote the ground state by E naught here. And let's consider like an optimized wave function that's close to the ground state, in that the amplitude with the ground state is like 1 minus epsilon squared for some small valued epsilon. And amplitude with the higher energy excited states, which I've denoted here by E perp. This contains all the high energy excited states. The amplitude of that state is just epsilon, some small value of epsilon. And well, you notice that the accuracy of the energy of other observables actually differ. So the deviation between the energy of this state and the ground state energy is O of epsilon squared. And that follows from the fact that the cross terms vanish when you compute this excitation value. And this arises because both the ground state and the higher energy excited states are orthogonal with respect to the Hamiltonian. So this equation here is equal to 0. But on the other hand, if we consider like an arbitrary observable, like magnetization or correlation function, that error scales as O of epsilon, because these cross terms do not vanish in general. And so we see that in general we have a quadratic discrepancy in accuracy, where the accuracy of the energy, or the error in the energy scales like O of epsilon squared, and that of an arbitrary observable is just O of epsilon. And so you might be in a case where you suffer like 1% error in energy, and you think you have a very good approximation to the ground state, but you could still suffer like a 10% error in another observable, and that sounds pretty bad. And that's kind of indeed what we see in this situation here. So the question we asked is, can we reduce the error in arbitrary observables from O of epsilon to O of epsilon squared? And this very much sounds like a job for randomized compiling, because this provides a quadratic suppression of error, which is exactly what we want. And the answer is, again here, yes. And how we do this is we sprinkle in a little bit of incoherence. And specifically what we do is we randomize over many neural network quantum states, each of which is a good approximation to the ground state. So I'll denote these again by an index j, so psi theta sub j. And we're going to average over a bunch of these neural network quantum states. Or we're going to do so in a very strategic way. And by averaging over a bunch of these states, we promote our pure state to a corresponding mixed state that I'm calling here rho sub theta. That's a probabilistic mixture of the density matrices corresponding to those pure states. And indeed, as I will show, it provides a better approximation to the ground state than any individual neural network quantum state psi sub theta. Now, the question remains is like, how do we actually realize this, and how do we keep track of all of these different neural network quantum states? And there's a kind of simple way that we can do this. So how we propose to do this is by using randomized real-time dynamics. Because if we're minimizing the energy of the Hamiltonian, we have access to it, and in principle, we can also apply time evolution to our state. And so what we do is we map our pure state, psi sub theta, to a mixed state that is a probabilistic mixture over time-evolved states that have evolved under the Hamiltonian. And so this corresponds to sampling at time t in this distribution p of t, and then evolving for that time t on the neural network quantum state. So what you do is you kind of like take the state that you have that should approximate the ground state, and you apply random amounts of real-time evolution on top of it, and that generates this mixed state here. And intuitively, why this might work in suppressing errors is that by applying real-time evolution to this state that again is close to the ground state, this imparts a relative phase on the higher energy excited states. Where this delta here is a spectral gap, that is the gap between the higher energy excited state energies and the ground state energy. And because the variable t is drawn from this distribution p of t, this phase is actually a random phase. And as is well known, random phases average out to 0 or to very small values. And so you'd expect that for a suitable distribution p of p, this could impart this random phase out here and suppress the contributions from the higher energy excited states. And this, at the end of the day, leave a better approximation to the ground state. And indeed, we can show that is the case by using this notion of randomized compiling. So again, I have the proof of this later in the appendix, but the punchline is that if we estimate observable with this state here, then it deviates from the true ground state value by amount O of epsilon squared. So that again achieves the same error scaling as of the energy. This of course does depend on the distribution P of t, and there's some conditions that need to be met. And again, I have this in an appendix slide for more details. But generically, you want a P of t that has a standard deviation that scales like 1 over the spectral gap. And the reason for that is that you want this random phase to vary from like -1 to 1. And in order for that to happen, your variable t, the amount of time you simulate over, should be like on the order of 1 over delta. And indeed, that is the case. You want the standard deviation to be sufficiently large so that that does happen. But even if you're in a situation where you can't choose a standard deviation to be that large, this still does suppress the error. And it's quantified by like a more in-detail theory that I have later in the appendix. But suffice it to say that we can choose a distribution that does quadratically suppress the error and afford better estimates of ground state observables. And of course, what remains is how do we actually implement this in practice? And as I mentioned earlier, in deploying neural network quantum states, we usually use variational Monte Carlo. And so what we can do is we can express our estimated observable in the state rho sub theta as a variational Monte Carlo expression. And we get this expression shown here. And what's interesting to note here is that this is actually just an average of ordinary variational Monte Carlo. So on the inside here, we're sampling configurations from the square of the wave function, and then estimating the local observable and taking the average over that. But there's this additional expectation value out here, in which you sample times from the distribution P of t. Okay? And in addition, the state psi sub theta is now the time-evolved neural network quantum state, and the local observable is the time-evolved local observable. But other than that, we're just taking average over variational Monte Carlo. So yeah, this is just a time average of standard variational Monte Carlo, as I mentioned before. Now, to actually realize this, one would be concerned about like, oh, do we need to keep track of like a bunch of different states that have evolved for different amounts of time? And kind of yes, but we can do so with just one single state. And the approach that we develop is, we've termed it dynamical averaging. And the idea is to take your state psi sub theta that you've already optimized, so you minimize the energy to the best that you can do, and you take that state and let it evolve in time, in real time. And as it evolves in time, you draw samples from it. And you aggregate all the samples together and use that to estimate your observable. So this differs from standard variational Monte Carlo in which you'll take your optimized neural network quantum state, and you'll just sample configurations directly from it, and then use those to estimate your observable. But here we're saying is take that state, and just let it evolve in real time, and as it evolves in real time, draw samples from it. And then take all those samples together and average them together to estimate your observable. So that's kind of where the name like dynamical averaging comes from. And we're taking the state, let it evolve dynamically in time, and then take samples from it and average those together. And indeed, we benchmark this on the mixed field Ising model, which is given by this Hamiltonian here, kind of close to criticality. And for our distribution, we choose a Gaussian. So it's a Gaussian distribution like this, and we want to compare the connected correlation functions with the exact solution, which if you remember from before, differed from the exact solution by like 10% error, which isn't too great. But fortunately, by using dynamical averaging, as I showed here in blue, we achieved much better errors, where now the errors have been suppressed from like 10% down to 1% by using our method. So hopefully this is like an indication that, yeah, like we can randomize our real-time dynamics to suppress the errors sufficiently in these arbitrary other observables. Now, there's a bit of discussion I do want to mention here, which is that our method sharpens the accuracy of arbitrary observables, so things like correlation functions and magnetization. But importantly, a disclaimer is that it does not improve the accuracy and energy because we're just revolving under real time. And when we evolve under the Hamiltonian, we can't change the energy. Or we can't change the energy. Fortunately though, the energy already has an accuracy, an error that scales to O of epsilon squared. So it's already as good as the other observables, and it can't really be improved. In addition, this method does require real-time evolution, which can be expensive in some cases, and more so than actually minimizing the energy. And so as a result, the utility of this method is really in situations where your energy minimization starts to converge or flatline, and you might think you've done like as good as you can get. You might think you have as good as you can get as of an approximation to the ground state. But you can actually do a little bit better by applying real-time evolution on top of that. And in addition, I do want to mention that this tool is actually more general than just neural network quantum states. So in principle, it does apply to other variational methods like tensor networks and even variational quantum algorithms. So this could also benefit from this randomization picture. So with that said, I can go into some conclusions here. Overall in this talk, I wanted to introduce you guys to this concept of randomized compiling. That is taking your state and rather than evolving under a single approximation, averaging over many of these approximations. And it showed you how this boils down to this kind of moral takeaway, which is if you want to approximate a unitary, use a non-unitary channel. And if you want to approximate a pure state, use a mixed state. And in doing so, you can do better than had you use just a unitary or a pure state individually. And we show this in two contexts, where in quantum algorithms, it reduces the cost of these quantum signal processing algorithms by a factor of 50%. And in classical algorithms, it improves accuracy of approximations to the ground state. And as I mentioned earlier, like kind of the punchline of this talk, these randomized algorithms are better than their deterministic counterparts, but they only use like a little bit of randomization. Like the states that we're randomizing over don't differ by that much. And so indeed, a little incoherence really does go a long way. Otherwise, I do want to mention that it seems like randomization is a very useful tool that could and should and is be adopted into quantum information. For instance, randomized compiling applies nicely to more general quantum Monte Carlo algorithms beyond just variational Monte Carlo. So things like path linear Monte Carlo can also serve to benefit from randomized compiling. And more generally, other randomized tools from linear algebra have really been useful in in computational mathematics and machine learning. And it feels like this is certainly an opportunity to integrate these tools into quantum information. And I think there's like a lot of really cool research that could be done in this direction. And with that said, thank you all for listening. And if you're interested, feel free to check out the papers. This one's not on the archive, but if you want to see it, I have a draft I can send it to you, so just let me know. But otherwise, thank you all.